Hello everyone. In the previous videos, we have been discussing the problem of a beam subject to lateral loading which induced only bending. In this video, we are going to make a modification in that we are going to consider, in addition to the lateral load, an axial load also. Now, this kind of a combined load is going to induce bending as well as stretching. So you see the situation here. This is our beam. We have the lateral load in the form of this distributed load Qx. And we also have, in addition, this axial load. Okay, the P here and the P here, it balances each other out. Now, again, you note that just like in the previous two videos, I have not depicted any particular boundary conditions. In fact, I have not even shown the two ends. So this general depiction, it represents or it covers various kinds of boundary conditions. So how do we address this kind of a combined loading situation? So the first thing that we are going to do here is that we are going to use the principle of stationary potential energy exactly in the same fashion that we had addressed the previous problem of only lateral loading. So going forward, what we are going to do here is first of all write down uh, the total potential energy pi, which we understand to be composed of the contributions from the internal potential energy and the external potential energy. We also note that this internal potential energy can be subdivided into a contribution from the stretching term or the axial load or the deformations due to the axial load, and the internal energy due to bending that is induced by the lateral load. Similarly, the external potential energy can also be subdivided into uh, the contribution from the axial load and the external potential energy due to the lateral load. All right. So what are the expressions for these individual potential energies? The V internal stretching, that is given by an expression which I had mentioned in the context of discussing the Castigliono's theorem on deflections in the previous chapter. So I request you to refer to that. So for a beam like this, where the loading or the external load is given by this P, the axial load is given by this P, E is the Young's modulus, and A is the cross-sectional area of the beam. This term represents the total potential energy, the total internal potential energy associated with the stretching. The next term is already familiar to us from what we had discussed earlier. It is simply the m square by twice EI integrated over the entire length of the beam. Now for the V external axial, we note that this will be basically just the negative of the work done by the given axial load. So if you understand that this P and this P is applied at the two ends, then all that we really have to write is this P multiplied by the displacement at the two ends. So for this, it will be P times the displacement at the x equal to L, and this one will be P times so we have to be careful about the algebraic sign here. So this will be minus P if we consider the x direction to be in this fashion. So if we consider our x to be like this, then this will be minus P times the displacement at x equal to 0. But even though we can write simply like that, what we are going to do here is to write this in a slightly deliberately more complicated fashion, and you will realize the benefit of that while solving problems where the axial load may not be actually be acting at the end of the beams, rather somewhere in the middle of the beam. Okay, keeping in mind such kind of general situations, we'll write down uh, the potential energy as associated with the axial load. We note that this is simply P, but this P is acting. So what we wish to write this is in the form of an integration. Okay, so even though so let me just write this down like this. So suppose I write it like this, that P times US evaluated at x equal to capital L. This US variable, it represents the deflection in the axial direction. So this is the displacement. This is solely due to the stretching term. The S represents that, and it will come with a negative sign. But I'm not going to keep this term like this. Rather, I'm going to, as I said, convert this into uh, into an integration form. Okay, so how can I do that? To see what I have done, I have considered this P times US, but I have considered this in the form of an integration. But at the same time, I have made it so that there is this uh, Dirac delta function, or this Dirac delta operator, which is uh, at x minus L. So that ensures that this multiplication is only going to be really applicable at x equal to L. Okay. Next, in a similar fashion, I want to take care of this end. So for that, what I would do is to write something like this. Okay, this minus P represents the fact that at this end, the axial force is in the opposite direction of the positive x sense. Now, of course, I don't want to keep it like this. I want to make it like this, an integration form. So all that I have to do is uh, to write the appropriate Dirac delta operator. That is x minus 0 simply multiplied by US. Please note that both in this integration as well as in this integration, this US in general represents the displacement due solely to stretching anywhere at between this 0 and L. But it is because of the presence of this Dirac delta here and this Dirac delta here that this term gets activated at x equal to L here and at x equal to 0 here. Okay, so much for the the external potential energy due to the axial load. The potential energy associated with the lateral load will be exactly the same as what we have discussed earlier in our earlier video. So that is simply minus times q w dx, this entire integration. This integration is from 0 to L over the entire length. All right, now you see this term is already familiar to us, this term is familiar to us, these two things are quite new, plus this is also new. Okay, now what we are going to do is uh, just like we had considered uh, the rewriting of this term in terms of the lateral displacement W, which is this W. Okay, so I request you again that if you have not seen the earlier video where we had used the principle of stationary potential energy on the lateral loading only, which induces only bending, you please look at that first, because I am going to utilize those expressions directly here. Okay, so uh, the motivation here is the same, that this term which involves the p, I again want to rewrite this term in terms of the US variable which is present here and which is present here, in much the same way that this m was written in terms of the w which is present here. So ultimately my motivation here, or my final goal here, is to obtain governing equations in terms of the deflection variables US and W. Right. So towards that end, I note that my P is basically this. So this is sigma xx integrated over the entire cross-sectional area. And that again considered a very simplistic kind of uh, material behavior, basically the simplest of material behavior, like the Hookean material behavior. We have this kind of a situation. So sigma xx is equal to Young's modulus times the epsilon xx, and you understand that this epsilon xx can be directly written in terms of the stretching variable us using the strain displacement relation like this. Please note that here I have not used any partial derivative because the only thing that us is varying with is x. Okay, so these are certain simplifying assumptions which are inherent in our derivation. Okay, uh, coming back to what I was saying, this is of course dA. Now this can be further simplified to EA us dx. The understanding here is that even though us may be varying along x, but over a particular cross section it does not have any variation. Okay, so this can be taken out of this integration. The E also can be taken out of the integration, so that we are just left with this integration over the entire areas, which is just the area itself. All right, so with this we can proceed, and we can write down the the expression for delta pi. Okay, so this is the part where we are going to use the principle of stationary potential energy. So let me just write this down once more, where I substitute uh, the appropriate expressions. So this is you understand that what I have done here basically is that if you look here, this p is Ea dus dx, but I have here this p squared by twice Ea. So when I substitute this expression back here, this I have e square a square in the numerator, and that cancels with this denominator to leave Ea. So ultimately what I have is half of Ea times this dus dx square. That is exactly what I have written here. Okay, next, for the term involving the bending moment, as we have done in the previous uh, case, for the case involving the only the lateral loading, we had seen that we had obtained this expression, half of ei d square w dx square. I'm not going to go into a discussion for this again. We've already spent some time on this, and the rest of the terms I'll just keep like that as before. So P Dirac delta x minus L us dx, and plus, because we have a minus and then a minus p inside, so that becomes a plus P Dirac delta x minus 0 us dx minus 0 to L Q W dx, close the square bracket, equal to 0. So whatever is there within the square bracket, we have to take the first variation of that. Now you please note that when we take the first, when we do the subsequent steps, you see that this first variation is going to be operating on these terms separately. Now if you consider just this term, whatever is going to happen here, we've already done it. We don't have to actually clutter up our space here, our writing space here, by repeating those lines. Okay, by repeating those terms, like this one and this one, they're exactly the same as before. All that you have to really do in terms of new effort is to deal with this term, and this term. So let us do that. Okay, so so for the first term, what I'll have is EA dus dx, then d delta us dx plus, I'm going to write this as same as before. Okay, because I'll end up with quite a few terms here. I don't want to clutter up my writing space here. Okay, uh, for this I have, for this term I have minus p delta, the Dirac delta, x minus L, then delta us. So please don't be confused by this delta and this delta d. This delta d is the Dirac delta. This delta of us, this delta is this delta, which is the first variation delta. Okay. And then of course I have similarly p Dirac delta x minus 0 delta us dx, and uh, 0 to L. This is also the same as before, but because this is such a short term, I'm writing it anyway. So this entire thing is equal to 0. All right. Now, all that I have not written here, it basically involves in the various steps. If you remember from before, a repeated use of the integration by parts, and the motivation there was ultimately to arrive at an integration term which would involve the first variation of the bending variable or the deflection variable w, because in this other integration term we have this first variation of w which does not involve any derivatives. So in a similar fashion, we motivate our subsequent steps of simplifying this expression with the understanding that we want to arrive, or with the goal that we want to arrive at an integration term which would involve the delta us, but which would not involve any derivatives like this. So we want to have a term like this, delta us which does not have any derivative, a delta us which does not have any derivative. Okay, so towards that end we carry out the integration by parts. So for the boundary terms, we'll have this this thing, EA dus dx delta us 0 and L, and then ddx of EA dus dx delta us dx. So now you see that here we already have this, the presence of this delta us, which is exactly what we have here and here. Okay. So we write the rest of the terms just like they are present in the previous step. All right. So what do we do next? Well, we can proceed in different fashions. Like, for example, we could have, uh, so, uh, uh, sorry, I have not written a very important thing, which is this term, which is the same as before. So I really need to write that properly. Let me do that. So what I'm doing is I'm writing this plus same as before. Okay. Uh, Actually, this term is also should have come under the same as before, but anyway, I'm going to write it separately. All right. Now you see, whatever is present in the same as before is basically just the boundary terms involving the delta W uh, or the W and one integration term involving the delta W. Okay, so what we had done earlier was to club that integration term with this term to obtain the governing differential equation. So that's the same thing what we can do here is to club this integration term with this one and this one to obtain a governing equation, which would of course involve this Dirac deltas. That is certainly one version that we could go ahead with, or we could choose to write this or obtain a slightly different version of this. Okay, so let's try this slightly different thing, because if we were to choose to go for the first version, then I mean it's just very easy and straightforward. You just obtain as a governing differential equation involving the coefficients of this delta us, this term with this term and this term. So there's not much to do there, but let's see what happens if we choose another version of it. That will be really interesting. So uh, what we'll do is we'll just consider this term and this term. Okay, so let's do that. We're going to consider this term and this term separately. So please note that what I'm going to write next is not the implied sign of this. Okay, so I'm going to write with a separate color also. So let's consider this. Integration 0 to L t times Dirac delta x minus L delta us dx plus, so this thing can directly of course be written, because at the very outset I had noted that this is simply this. The only difference is that back then we did not have the involvement of the first variation that is present here. So uh, the same thing for the second term. So that overall this can actually be written as in the form of boundary terms. Okay, so what I was saying earlier uh, is this is basically this, that if we were to proceed uh, directly from this term, I mean clubbing this integration, then we would obtain as our governing differential equation uh, the coefficient of this delta us, which is this term, and then we would have this p times the Dirac delta of x minus L and this p times the Dirac delta of x minus 0. So this p and this p would be present in the governing differential equation itself. However, in this version that I am proceeding right now, you see what has happened is that I have managed to write these two things in terms of these boundary terms, so that subsequently what is going to happen is that this is going to get clubbed with this term. Okay, so if you have any confusion, you pause the video and maybe take a moment to realize what is going on here. Okay, so in this version we are going to club this with this. All right. uh, and And whatever was happening before involving the W terms, that is going to remain the same as before. We don't even have to worry about that. And in fact, I'm not even going to write that. Okay, it is exactly the same as before. I'll just deal with these terms involving the US. Okay, so going to the next slide, uh, what we have is uh, EA, the US, dx, delta US is boundary term. Then we have this integration term. Please note that in the previous slide I had this ddx of EA dus dx. I'm considering that E and A are independent of x, so that in the next step that I'm just now writing, I'm writing this as EA times d squared US dx squared. And then I have these boundary terms which I have just derived in the previous slide, plus instead of writing same as before, what I'm going to write is all terms involving W. Okay, this is equal to 0. Therefore, the governing equations are EA d square US dx square is equal to 0, because you note that here we don't have any other integration term. I have missed something here. Should be with a delta US. Now it's right. Okay, so there is no other integration term which involves this delta US. Had we kept this term in the form of the integration, then certainly there would have been, and then we'd have, instead of this 0, this p Dirac delta x minus L and a minus p delta Dirac delta x minus 0. But those things are not present because I have converted those integration terms into these boundary terms. So they'll be present in the boundary terms actually. But let us not forget that these governing equations also have contributions from these terms involving the W, and that we have seen earlier was this EI d4 W dx4, and that is equal to Q. And for the boundary conditions, what I will have is this term clubbed with this term, so that I need to write this as, at just like before, at x equal to 0 and x equal to L, I have uh, either EA dus dx minus p is equal to 0, or US is specified. I again emphasize that it is extremely important to write this in this proper fashion. Okay, please note that because that we have the presence of this delta US term, it is US which needs to be specified as part of the boundary, but US itself does not need to be 0. In addition to this, we'll have again uh, at x equal to 0 and x equal to L, the terms involving the W. So, so just to make things clear, what I'll do is I'll go back to the slide where I had mentioned those and point out those to you. Okay, so this is what I'm talking about here, right? So I had this thing. Let me see if I can actually copy this thing out. So this, along with whatever else was present here, which is this one. Okay, so at x equal to 0 and x equal to L, what I can do is I can write this in slightly more uh, feeling fashion. It's like this. These are our boundary conditions. At x equal to 0 and at x equal to L, we have, in addition to whatever we had earlier in terms of the W, this extra boundary condition involving the US. Okay, so this EA dus dx is equal to P, either that or US is specified. So these two equations are the governing equations, and these are the things which will act as our boundary conditions. So together, all of them together, they are the desired equations for our mechanical system. Now, it is very, very important to note one critical thing. All throughout our discussion, we have found it very convenient to talk separately about the US and the W. And this is the hallmark of this derivation, that the stretching and the deflection can be dealt with in a separate fashion, like completely independent or decoupled from each other. Okay, quite independent from each other. And this is exactly uh, the simplifying thing that we have done, which will get us into trouble when we consider, instead of stretching, some kind of compression. As I had pointed out and emphasized in the first video of this beam theory chapter, that overview and prelude, uh, the issues associated with buckling. So this kind of a theory, it will be because this the stretching and the bending, they are decoupled from each other. uh, it'll get us into trouble, because it is not going to enable us to address issues involving buckling, but we'll see that later. So the idea is that in the next video we are going to take another look at the very same problem that we have done in this video, but we'll address it from the point of view of the principle of virtual work. Thank you very much.